In the first example, we're given a total time for an echo to hit a cliff and come back in 1.44 seconds. Okay? And we are told that the temperature, I probably should put a lowercase t for that. That starts to get confusing. So T total, lowercase t is time, capital T is temperature. And the temperature here is 6 degrees Celsius. And the question we want to know is, first of all, what is the velocity at this temperature? 6 degrees Celsius, I put it down there. What is that? And then what is the distance between you and the cliff? Okay, now I'm going to show off my great artistic ability. You're going to love this. So you're standing on a cliff or on some kind of platform right here, or maybe even just like the bed of a river. It doesn't have to be high. But then you speak. Now, we've got this gigantic cliff over here. Let's say we're in Dover of England, or Cliffs of Dover. Beautiful white cliffs of Dover. And as you speak, they collide with this barrier here, and they come back at you. And then you pick that up. And that's how echoes work. So, according to this, the time it took for it to go to the wall or to the cliff and back was 1.44 seconds. But since it took half of that time to get to the wall or to the cliff, we're going to look at the half of that. So 0.720 seconds is what we're going to use in order to figure out how far away that cliff is. So we're going to use t sub 1/2, which is 0.720 seconds. Now, the next thing we need to figure out is how fast is the sound going at 6 degrees Celsius. Well, with that one, we're going to use 331 meters per second plus 0.6 times 6 degrees Celsius. Type that in your calculator, you get something like 334.6. Round that off, that becomes 335. And 0.6, by the way, is meters per second per degree Celsius is the label for that. I forgot to mention that in there, but that is the label. That's why things work out. The degrees Celsius cancel out to leave you a sum of 2 meters per second, which will be in meters per second. So we know the velocity of this thing is 335 meters per second. So boom, you speak, 6 degrees, a little chilly in England, it always is. It's right on the ocean there. And so the speed of sound does increase, but a little bit, but not a whole lot. And if we want to find that distance there, then we're going to have to use that velocity equation that uses time instead of frequency. So instead of using distance times wavelength, it's going to be distance or length rather than distance times frequency. We're going to divide it by time. All right, so we're given here 335 meters per second is equal to, and the distance is what we don't know, over, and the time we do know is 0.720 seconds. Now, we also could have derived the equation before we even did this, and just by flip-flopping the time and the velocity here, I'm sorry, we don't need time. We need the distance. So we could have just multiplied t by this. So we could have used the formula d equals vt, which is what you're going to get when you end up doing this algebra here anyway. But this would be 335 meters per second times the time, 0.720 seconds. Either one is fine, doesn't make any difference. But regardless, your answer is 241 meters. Okay? So, some moving parts there that you need to be concerned with. Temperature to change to the velocity of air at that temperature. And then using the formula D equals VT, or V equals D over T, and use your algebra splits for that. Oh, and also taking half the time, because the time that you hear it, it's actually taking 2 times the time that you need it. You only need half of it, so we take half of that. Next example, we're trying to find the time for this one for a rail. You say take a hammer and hit a rail, and somebody is a mile away, and you have a phone system where the person says, I'm going to start, and you hear the sound hit there, and then how long does it take for it to be heard, and so someone with a stopwatch, listen to that, will stop at that point. So what would you anticipate that time to be? Well, we know that we're told here that this is an iron rail, and that's important because now the medium instead of being air is iron. And for that information, you need to go to page 494 in your book, where there's a chart of series of media that has various times for velocity of sound. Okay, and we'll get back to that in just a little bit. So we know the distance is 1 mile. And we want to figure out the time from that. So we need to find the velocity. And that's what that's going to come from, or the velocity of iron. Now, we're saying this at 0 degrees because the calculation for the change of velocity is not the same as it is for air. So we'll just say it's a cold day. Okay? So, if you look at the chart on page 494, the speed of sound in iron is 4,500 meters per second. That's incredibly fast. That means that because of the closeness of all the iron atoms that are trapped in the rail, the bumps that they're going to have are going to be really, really quick. So as the sound disruption occurs at one end, the transfer of energy is really easily taken across, which is one of the reasons why metals are really good at conducting heat and electricity for the very same reason. Okay? Or pretty well with the heat part. Electricity is more about electrons, but it's the same basic idea. All right, so now we're trying to find time. So we know that velocity equals distance over time. And since we're trying to find time, we can just flip-flop these around, and time is going to equal the distance over velocity. Well, we got to find the distance, don't we? So let's go with this 1 mile. Now, one of the conversions I've given you in the past, and Kim, is 1 kilometer is 0.621 miles. You can use whatever conversions you want. You may find one otherwise, on the phone or in the book or whatever. The book has a whole bunch of conversions on the front or back flap, depending on what you're looking for. But I'm going to use my old system here. So we're told that 1 kilometer is 0.621 miles, and then time rather, and then to change 1 kilometer to meter. There's 1,000 meters in a kilometer. And when we work that out, that becomes 1,610 meters. Which makes sense. And those of you who run track know that a mile is considered 4 laps around the track, which is 1,600 meters. So it's actually 10 meters past that point is a true mile. But regardless, that's our distance. Our velocity is at 4,500 meters per second. And so you divide that out, you find out that the time it takes from that hammer hitting the rail to the person hearing the sound after that hammer is struck is only 0.357 seconds. A third of a second. That's amazing. So, practice problems. We have 5 practice problems here, all related to the same kind of problems, same situations, relationship of time, distance, and volume. Have fun.